Hello, our group will be presenting our project titled Multi-Class Image Classification, Plant Disease Detection with Transfer Learning. In this project, we focus on how deep learning and transfer learning can be used to automatically identify plant diseases from images. This is an important real-world problem because early and accurate disease detection can significantly reduce agricultural loss and improve plants' health. Our work spans the entire pipeline from parallel data cleaning to model design, training, and architecture evaluation. This project was completed for Data Science 3000 for 2025. Our team members are Junjie Mo, Minhong Xu, Junsheng Liang, Guanling Zhu, and Zhenyan Yuan. We will walk you through our dataset, methodology, model architectures, experiments, and key results. Here we show a sample of the images from our dataset. As you can see, all images are leaf photos, and each leaf belongs to one of the many disease classes. The dataset includes a variety of colors, texture, and shapes, which makes the classification task more challenging but also more realistic. Before training, we applied several pre-processing steps and data augmentation techniques. For the training set, we resized all images to a fixed input size and then applied random horizontal flip, random rotation, and color jitter. These augmentations help the model generalize better by simulating different lighting conditions and leaf orientations. We also convert the images into tensors and normalize them using the standard image net mean and standard deviation, since our transfer learning model were pre-trained on ImageNet. For the validation set, we only resize, convert to tensor, and normalize. We avoid augmentation in validation to ensure the evaluation is consistent and fair. Overall, these per-processing steps makes the dataset cleaner and help reduce overfitting during training. At first glance, our dataset appears quite large, with over 35,700 images. However, wall size can be misleading. Once we analyzed the dataset more carefully, we discovered two major issues that would seriously impact model reliability. The first issue is severe class imbalance. On the right, you can see the class distribution. Some disease types have close to 3,000 images, such as tomato virus, while others, like potato healthy, have only around 150. That's roughly a 21-to-1 imbalance. A naive model trained on this distribution might simply learn to always predict the majority class and still achieve high accuracy, without actually learning the underlying patterns. The second issue is toxic duplicates, which we will talk about on the next slide. So overall, although the dataset seems large, its quality issues, both imbalance and redundancy, mean that cleaning and rebalancing are essential before any meaningful model training can happen. As we mentioned earlier, many duplicates in the dataset were not simple file copies. Standard methods like ND5 hashing were not enough because many duplicate images had slightly different metadata or small compression differences, meaning ND5 treats them as different files. To adjust this, we implemented phash in our clean pipeline. Unlike cryptographic hashes, phash generates a fingerprint based on the virtual content of the image. So even if two images are stored differently or slightly compressed, as long as they look the same, their phash will match. Using p-hash allowed us to remove 339 virtual duplicates. This ensured that our training set and evaluation set were truly distinct, which is essential to avoid data leakage and inflated accuracy. We also uncovered a major issue we called toxic duplicates. Like we just mentioned in the last slide, there are cases where the exact same image appears in multiple classes, labeled as different diseases. We found 160 of these cross-class duplicates. If we trained the model on them, the model will be punished regardless of which label it predicted, because both labels exist. This creates contradictory guardians and directly harms the decision boundary. So p-hash not only helped us clean redundancy, but also revealed hidden labeling issues that makes the dataset fundamentally unreliable unless corrected. To combat class imbalance, we explored mix-up augmentation with alpha 0.2. Mix-up blends two images and their labels. For example, 80% of one class and 20% of others. This prevents the model from memorizing small classes and encourages smoother decision boundaries. Although mix-up wasn't part of our final implementation, we built support for it and tested it. EfficientNet ultimately benefited more from when argument and a weighted sampler in our best results. Our experiment focused on one question: how much does ImageNet pre-training help? To test this, we create a 20-layer CNN trained from scratch as our baseline. It learns only from our dataset with no prior knowledge. Then, we compared it to two standard transfer learning models, ResNet 50 and EfficientNet B0. This setup allows us to clearly evaluate the benefit of reusing pre-trained virtual features versus learning from scratch. These training curves reveal the most important insights of our entire project: the power of feature reuse through transfer learning. Let's start with ResNet and EfficientNet. Both models reach over 90% accuracy in just the first approach. This immediately convergence tells us something remarkable. The low-level features learn from generic everyday objects, such as edges, corners, and textures, transfer almost perfectly to plain leaves. In other words, transfer learning doesn't just help, it gives us a massive head start. Now compare that with our custom CNN20. It begins at only 9% accuracy, which is basically random guessing across our 26 classes. It took almost 30 full approaches for the scratch model to finally reach 90%. We also see much higher variance in its training and validation curves, showing that the model is struggling to stabilize without pre-trained features. This contrast highlights a key conclusion. Even though the dataset has over 35,000 images, it is still not large enough to reliably train the deep 20 layers network from random initialization. But pre-trained models, on the other hand, require almost no warm-up and immediately lock onto useful patterns. So the takeaway is clear: feature reuse is incredibly powerful, and transfer learning dramatically accelerates convergence while improving stability and accuracy. Our results show that EfficientNet B0 performs best overall. It achieved 99.79% accuracy, slightly higher than ResNet 50's 99.38%, and far ahead of our Scratch CNN at 19.40%. Ethernet also produced the lowest validation loss. Importantly, it does all of this with far fewer parameters, showing that modern compact architectures can outperform others, heavier models for tasks like plant disease detection. The confusion metric shows that the custom CNN doesn't make random mistakes, it makes semantic mistakes. It often confuses tomato early blight, late blight, and target spot diseases that all appear as brown lesion with very similar textures. Without pre-trained feature extractors, the Scratch model cannot capture these subtle differences. This explains why transfer learning models outperform it on fine-grained disease categories. If we only looked at the custom CNN's best one of 90.4%, it might appear acceptable. But once we applied five-fold cross-validation, a very different picture emerged. The custom CNN showed a standard deviation of 7.18%, which is extremely high. This means its performance is unstable and heavily dependent on whether it gets a lucky chain test rate. In other words, the model doesn't generalize well. In contrast, Ethernet demonstrated a standard deviation of just 0.1%, and WestNet remained similarly stable. These low variances shows that pre-trained models aren't just more accurate, they are far more robust and consistent across different folds. You can also see this in the fold-by-fold results. Ethernet and WestNet stay tightly grouped around their average, while the custom CNN swings dramatically between folds. So the key insight here is that single-one accuracy can be misleading, but cross-validation reveals the true reliability of each model. In conclusion, Ethernet B0 proved that parameter efficiency beats raw model size. Despite having only 5 million parameters, it outperformed our 180 million parameters CNN and showed far greater stability. We also saw that training from scratch is unstable and impractical with only 35,000 images. Transfer learning is essential. With 99.8% accuracy and no compute cost, Ethernet B0 is ready for real deployment. Future work will target the remaining semantic errors, especially with the tomato blight subclasses. This is the work our team accomplished. Thank you so much for listening.